Hi everyone, I am Divyanjali. In this talk, I am going to present our recent work on partial order based thread modular analysis of release acquire concurrency. This is the layout of the talk. The objective of the present work is to design an efficient and sound reachability analysis of C programs under release acquire concurrency. Before we get into the details of our method, let's understand some background concepts. In this work, we are focusing on array memory model. The array memory model is axiomatic memory model, that is, it is defined using several relations. First, we have sequence before or SB relation. This relation is an intra-thread relation over instructions that must happen in same order in every execution. Here, the pairs W1x and WY are in SB, and from thread 2, RY and W2x are in SB. Next is MO or modification order relation. This is a total order over stores to the same memory location. Every valid array execution must have a valid MO for all the program variables. In this example, we have two stores W1x and W2x over variable x and one store WY over variable y. Hence, we have two possible modification order for x, W1 before W2 or W2 before W1. And we have only one possible modification order for y, which is W. Next is synchronizes with or SW relation. This relation forces happens before over operations from different threads under certain conditions. In this example, we have two stores W1 and W2 and one load R over variable x. If Rx reads from W1x, array memory model forces an SW from W1x to Rx. The synchronization here means that everything that is sequenced before W1x should also happen before Rx, and everything that is sequenced after Rx. On the other hand, Rx did not read from another store W2x, hence there is no SW between them and no such restriction over HB is placed. Some might ask why we need an array specific analysis. To answer the question, let's look at the IRIW example. Here and in all upcoming examples, we will assume that global variables are initialized to 0. An interesting execution of this program is when C reads 1, D reads 0, E reads 1 and F reads 0. In such an execution, we have RFs from A to C and B to E. These RFs will cause SW in case of RA, and hence everything that is sequenced before A should also happen before C and D. Since there is nothing sequenced before A here, this is trivially true. And same conclusion can be drawn for B, RF, E. While in case of TSO, PSO or RMO memory models, FR relation is a subset of HB. This results in a cycle A, C, D, B, E, F and back to A. Clearly, this is an invalid execution under TSO, PSO and RMO, and hence the valid executions under TSO, PSO and RMO differ from RA memory model. That's why an analysis which is sound for TSO, PSO and RMO will be unsound for RA memory model, and that is why we require an analysis which is capable of handling RA memory model. Let's try to look at the landscape of verification techniques for RA memory model. First, we have VBMC. It is bounded in terms of number of view switches and hence cannot explore the entire state space. There are some logic and proof frameworks, but they all require human intervention. Some runtime techniques have been proposed over past 4 years to analyze the RA programs, but they limit the analysis to a fixed input. Clearly, all of these techniques limit in their capability. Our current work is an effort to fill this gap by providing an efficient and sound verification technique. We are proposing a thread modular technique for verifying RA programs. So let me give you a brief overview of thread modular analysis. Thread modular analysis analyzes each thread independently in presence of a set of interference. The set of interference is a summary of how other threads can affect the execution of current thread. Here we first analyze thread 1. Since initial values of variable x and y are 0, at the beginning of T1 the program state has both x and y set to 0. When x equals to 1 is executed, the value of x is changed in the respective program state and we get an interference with value of x set to 1. This interference can potentially affect execution of some other thread if that thread reads from x. Next, we analyze read y. Since we don't know about any interference so far, the value is read from the current state and the program state remains the same. Next, we analyze thread 2 in similar fashion. While analyzing y equals to 1, we get the interference that can change the value of y. Now, we have some interferences that we did not use in the last iteration. It means that if one of the load reads the value from interference, we might see a new reachable program state. Hence, we repeat the analysis again and this time with the present set of interferences. Now, the initial state remains same. X equals to 1 changes the value of x and generate the same interference as it did last time. When read y comes, we know that this time it can also read from this interference. Hence, in this program state we have value of y which can be either 0 or 1. Similarly, thread T2 is analyzed. In this iteration we find no new interference and hence we will not be able to reach new program states if we repeat this analysis. That is, we can say that we have reached the fixed point of analysis. In our present work, we are proposing a thread-modular analysis for array concurrency that uses a novel partial order domain. We have established the correctness of our method and we have implemented it in a tool named poet. Let's have a look at the results of poet. We have implemented an interference combination based technique that was proposed in Cosano and Wang's 2016 and 17 works along with our partial order domain for array. This was done to compare the two techniques for same memory model while using the same abstract domain. The comparison of result over poet with this technique are shown here. All of these benchmarks are mutual exclusion benchmarks designed for sequential consistency. Hence, they are buggy under array. As you can see here, poet is consistently faster than the analysis using interference combination. This slide shows the comparison of same interf combination plus MO poset technique with our poet for the programs that are correct under array. These versions of mutual exclusion algorithm have read, modify, write operations working as fences to ensure the mutual exclusion. The performance of poet is significantly better here, especially on the bigger benchmarks. Here we compare the results of poet with VBMC over buggy benchmarks. We ran VBMC with a bound of view switches set to 2 for all of these results except for the last one where it is set to 3. The reason is that VBMC is not capable of finding the bug in Peterson 3 benchmark when view switches are bounded by 2. As you can see here, poet performs better than VBMC in all of these benchmarks. Here we show the comparison of poet with VBMC over non-buggy benchmarks. Remember that VBMC is a bounded technique. Hence, the inability to find the bug does not equate to the proof of correctness, while our results shows the time taken to prove the correctness of these benchmarks. Poet outperforms VBMC over all of these benchmarks as well. With this understanding of the problem, we will give an intuitive explanation of our technique. Let's start by discussing the proposed partial order domain. As we discussed earlier, every valid array execution should have a valid modification order per variable. In this example, we will look at the set of executions that will result in R1 equals 4 and R2 equals 1. This set of execution can have two possible modification order. First is where A is ordered before B, E and F, B is ordered before E and F, and E is ordered before F, that is a linear order A, B, E, F. Let's call it MO1. The second possible modification order MO2 is a linear order A, E, B, F. Hence, we can use this set of modification order to represent all the execution that results in R1 equals 4 and R2 equals 1. Next, we propose to abstract a set of linearly ordered modification orders as partial ordered set. For example, a set of modification order consisting of MO1 and MO2 from previous example can be abstracted to the partial order in which A is ordered before B, E and F, B is ordered before F, E is ordered before F. Note that B and E are unordered in this partial order. Here, the mathcal T represent a set in which each element is a set of MO sets, and mathcal T represent a set of partial orders. We define an abstraction function alpha from T to P and a concretization function gamma from P to T. We try to abstract the partial order further by asking the question if we need all the stores in partial order at all times. Let's understand this with an example. In this example, if C reads from B, D cannot read from A. Otherwise, it will be reading an stale value of variable x. We achieve this by knowing that when C reads from B, it observes the modification order in which A occurs before B, and the D has to observe at least this modification order. Hence, D also observes modification order in which A is ordered before B. Note that SB is a part of MO. It means that if any operation observes B in the modification order, that information is sufficient for us to know that it has also observed A. Yeah. So, we remove a store A from modification order if the modification order consists of some other store B which is sequenced after A in the program. We call this abstraction alpha sharp. The following result proves the correctness of our approach. First, we prove that the set T along with an ordering relation forms a poset. Next, we prove that the set of partial order P along with an ordering relation and some operations that we have defined over it forms a lattice. Theorem 1 states that the abstraction function alpha and concretization function gamma establishes Galois connection among these two sets T and P. Theorem 2 states that alpha sharp abstraction of forgetting older store operation is indeed a sound abstraction. We have excluded the proof of these results from our presentation in the interest of time. With the understanding of our proposed abstract domain, we now see how we use this domain in our analysis. Since RA memory model forces one modification order per memory location, we take one element from our lattice of partial order per memory location. Let's understand the intuitive working of our method with this example. Here, we are interested in the execution in which C reads from B. Hence, we will show the program state corresponding to this interference only. Initially, the modification orders are empty, so we start with POX and POY set to 5. When a store operation is executed, it will be added to MO. So, when A is executed, we append A to partial order with respect to X. Similarly, when B is executed, the partial order of Y is changed to B. When C reads from B, the modification order observed by C should preserve all the ordered pair in the modification order observed by T2 till C at this point and by T1 after B at this point. Hence, we merge these two program states together when an interference is applied. In this example, the program state prior to C is empty. So, when these two are merged, we get same program state as that of B here. In some cases, it is possible that program state before load operation and the program state after interfering store operation cannot form a valid modification order. That is, the two partial executions leads to an invalid execution under array. Hence, for load operation, we first check consistency and extensibility of the modification order. If these checks are passed, we merge the two program order. When we analyze D, the consistency and extensibility checks tells us that the effect of A are already in the modification order. Hence, a read of variable x here should observe the result of A if or any later write. Hence, in other words, we can say that value of x cannot be read from init in this program state. In the previous example, we did not see the advantage of our second level abstraction alpha sharp. Let's take a look at the following example to understand how it affects our analysis. For the current purpose, we will not look at the execution of entire program, but we will look at the program states reachable after instruction F under different set of interferences. This first figure shows the reachable program state after F when C reads from A and E reads from B. The box on the left shows the program state without taking alpha sharp abstraction, and the box on the right shows the program state with alpha sharp abstraction. The second figure here shows the program state under a different set of interferences where C reads from current state and E reads from B. Note that the program state under alpha sharp abstraction here is same as that in the first figure, while the program state without alpha sharp abstraction are different. Similarly, in third set of interferences where C reads from B and E reads from current program state, we reach the same program state with alpha sharp and different program state without alpha sharp. The fourth one where C reads from A and E reads from current program state reaches different program states with and without alpha sharp both. Hence, when we use alpha sharp abstraction, just like any other abstraction, we reduce the number of program states. In this case, we reduce the number of program states to 2 from 4, which results in improved efficiency of the analysis. Since alpha sharp abstraction is removing some information from the partial order, using it will surely introduce some imprecision. If a program property relies on the order of forgotten stores, we might not be able to prove it. But if we can figure out these stores beforehand, we can keep them in our partial order and recover sufficient precision to prove the property. For our current work, we consider atomic read, modify, write operations to be critical because these operations are generally used as fences in array programs. In general, other operations can also be critical, but that is out of the scope of this work. In the present work, we have proposed a new partial order domain over modification orders to construct a thread-modular analysis technique for array memory model, and we have proved its correctness. We have also implemented our technique in a tool named Poet, and that shows very promising results. In future, we are planning to use the proposed domain for other memory models such as TSO, PSO, RMO and C11 as well, and we are planning to find a way to discover critical operations as we discussed in previous slide based on property of interest and the programs automatically. Thank you.